So let's talk about the solution of quiz 2 first. We have two solid shafts. The radius are given. One is the diameter, 30 and 20 millimeter. And material property show just they're given the same material for both AB and CD, these two shafts, and allowable shear stress also the same. Radius of the gear E and F, one is 50 millimeter, one is 125 millimeter. Length AB, length CD, they're given. What is the maximum torque can be applied? And for these two shafts, AB and CD, the maximum torque determined by which one has maximum stress because the allowable shear stress for both sections, because the same material, allowable shear stress for both sections, they are the same. So whatever shaft that reach this allowable shear stress first, it determines what the maximum torque can be applied. So let's try to figure out which shaft has higher shear stress. So of course, tau equal to Tc over J. For the T, C and J, CZ is already given. Radius is given, diameter is given. So torque equal to force times the radius of the gear for the relation of these two, for the torque in these two shafts, A, B, and CD. We know that when the two gears coupled, the force applied by E to F and the force applied by F to E, this force, they should be equal magnitude, opposite direction. So these two F should be the same. And the only thing different is the radius. So this will create a difference in the torque in the AB shaft and CD shaft. So now we know that, let's assume that the force between the E and F we just put as F. And so this is the torque in CD and torque in AB, or you can say it's torque in E and torque in gear F. So now we know that for CD shaft, it has high torque and it also has lower radius. So Tc over J, J the function of C. So this is after we simplify the equation. So it's T over C cubed. And for one shaft, it has higher T, has lower radius. So of course, we know that without calculation, we know that the maximum shear stress in CD is definitely higher than maximum shear stress in AB. So we only need to consider CD because CD will fail first, right? CD fail first. So now based on CD will fail first, or CD has higher shear stress than the AB, we can calculate, well, tau equal to Tc over J. So T equal to tau J over C, tau J over C. The maximum torque is when the tau max equal to tau allowable. And this is J over C. Any question for this one? No question? How did CD fail first? Because maximum shear stress equal to Tc over J. J is half a pi C to the fourth. So this one C is gone. So this becomes the equation. And for the torque, we know that torque CD equal to 125 F and torque in AB is 50 F. So we definitely know that the torque in the CD section is greater than AB section. And for the radius, radius of CD equal to 10 millimeter, radius of AB.
It doesn't look like you.
Sorry. Let me turn off my phone.
You'll need to unlock your iPhone first.
Put it away.
Super movie.
So for this equation, we can see that if the torque in the CD is higher than AB and the radius of CD is lower than AB, of course, the shear stress, the maximum shear stress in CD is definitely higher than maximum shear stress in AB section. Does this make sense or not? Yeah. Any other question? Okay, so if no question, we can continue with the class last time. So in the last class, we talk about pure bending, which is simple situation for the bending when the bending moment is constant for the whole section. Yes, of course. Without this part, how do you know CD will fail first? You give me some explanation. How do you know? You cannot just guess, right? Okay, I guess CD fail first, so let's use CD for the calculation. Or I guess AB fail first, I use AB. Of course, if you guess AB, then you get 0 point. But without this part, how do you know CD fail first?
I think I did like the max tension on both of them and then found like the resultant tension from that and like
Well, not tension, shear stress.
I mean torque, not tension, torque. Like if the max torque on like section
CD is greater higher than AB.
yeah, like the tension on CD was like 28.3 Newton meters. That's the max. So then the tension on AB through that like top calculation would be 94, which is less than, or which would be 11.3 Newton meters, which would be less than 95.4 Newton meters, which is the max for
Don't
tension.
say the numbers because the numbers
Oh
confuse
yeah,
Just like big picture. What's your like big picture?
I basically just found the max torque for each section, and then I used those two torques to find like what would the torque be for the next.
How can you find the maximum torque in each section? I mean, the force is not given.
Because you have the shearing force and the radius.
Shearing force. There's no shearing force.
The max, what's the tau?
Shear stress.
Shear stress, that's what I meant.
Okay.
Like for that, for the second equation on the sheet.
The second equation.
It's like basically the same thing, just in a different order.
This equation?
Yeah.
So
you
just want to calculate torque and
yeah, and then you can use like the first or the one that you drew where the tensions are like related to each other.
tension related to each other.
Like I don't know, I got the right answer.
I still didn't understand. Let's say your first step is you assuming this is tau allowable shear stress, and you calculate this one for AB section, calculate this one for CD section.
Yeah.
And
then the torque will be related for the BC section or for the AB section, and then for the CD section, the opposite one using like the related torque will be the torque over the radius times the different radius. And
You
then
have
if it's less than the max, then it's allowable. And then you choose that one instead.
if it's less than max, it's allowable. What is less than maximum of what? I'm still confused. What we are comparing what? Stress, force, torque. I don't know what less than what? Allowable
less than the max torque.
maximum torque.
Yes.
The maximum torque is not given. The maximum torque is you need to calculate.
Well, I did calculate it.
Let me. So your first step is T equal to tau allowable J over C. So you calculate the tau, the TAB and TCD. If they both reach allowable shear stress, what is the second step?
Then you can take from like the max allowable for TAB, you can calculate what the torque will be for CD, and I called that like CD prime.
Sorry, could you please repeat that sentence?
So TAB, or I called the torque for like the CD section CD prime, then it's TAB divided by RE times RF.
Okay.
Yeah.
So you have the ratio.
Essentially, yeah.
So if the ratio lower or higher than anything, oh, wait.
I don't really think maybe this isn't important, but I did get that answer.
Get the correct number doesn't mean your method is correct. Because first, when you're doing this
And
one,
I used both equations. I think I just did it in a different order.
listen to me.
Yeah.
We rate everything based on understanding. I need to figure out what's your logical thinking here, because here you first assume that both of them reach the maximum shear stress for both, but for these two shaft, it does not reach maximum shear stress at the same time. One will reach first, one will be lower. So
Yes.
and second, this equation itself is correct, but what do you use this one for?
It's hard for me to explain, but my work is like I compare where like which one is gonna like which torque will be too much.
Mm.
And it will break the shaft.
Let's talk during the office hour.
Yeah.
Yeah, I need to check your work in detail to know what's your logical thinking. Because I need to see your detailed submission first to know. But having the correct final number, I'm not saying that you're wrong. I'm not saying that, but a general rule for grading all the assignments this semester, having the correct final number does not necessarily mean that you get full credit. I'm not saying your method is wrong. I need to check in detail later. But for this one, we do need to figure out which one fail first. You may have different method to figure out which one fail first. I would consider this is a reasonable way because we know that shear stress determined by torque determined by C. So if we know that a torque is greater ACD greater than AB for the radius CD is lower than AB. So based on these three, we definitely know that the maximum shear stress in the CD section is greater than AB section. Gear ratio. So let's answer the question in the chat first. Do we need to do the first part to get free? Yes. The second question, gear ratio. Purely based on the gear ratio, it can only prove that the torque in the CD section is greater than the AB section. But again, shear stress determined by the torque, also determined by the radius. I can have the CD has a higher torque than AB. I can also have a CD radius much higher than AB radius. In that situation, I can have higher shear stress in the AB section than CD. Make sense or not? Shear stress, the gear ratio only proves that torque is larger. It does not prove that shear stress is larger. For comparing the shear stress, you need to compare the torque and radius. Just one of them is not enough. If I got the right answer on paper but did not circle the correct answer, I got T, but I circled the wrong answer. Well, of course, there will be penalty on that. Any other question for this part? Okay. Let's move on to our content in last class. So in the last class, we talked about pure bending, and we based on assumption that plane remains plane, no warping or deformation of the plane itself, and the angle, this angle maintain 90 degree. This is our assumption of our derivation. So we got the shear stress equal to 0, shear strain equal to 0, and also since there's nothing really applied in the y and z direction, there's only a couple applied, sigma y and sigma z equal to 0. So in our pure bending situation, we only have one non-zero stress component, that is sigma x. And we talk about that the concept of neutral surface is where the strain and stress on that surface equal to 0 on that specific plane. And below and above that, if you bend it in this way, should be compression. Below there should be tension. And neutral axis can consider its line if for every cross section you have this point and you connecting this point for all the cross section, it becomes a line, and that line becomes the neutral axis. And this point is generated by having the neutral surface and the plane of symmetry, right? So this one is neutral surface on the cross section, and this one is a plane with symmetry. So now there's a point, the intersect point, and for every cross section, if you connect in this point, and this line becomes a neutral axis. And for the based on the strain definition, we have delta at different point equal to negative y times theta. So the strain equal to delta of origin length, so equal to negative y over rho is the radius of curvature. So basically, you can imagine that when you bend a beam, and this arc, you can consider is a part of a circle, and the radius of the circle, if you consider calculating from the neutral surface, becomes the radius curvature, and this is a rho here. If you see in the graph, this is the rho. If you consider the beam bending, it's just an arc, and if you put a full circle here, there's a radius. So radius curvature of the beam bending. And for the sign, of course, above neutral surface, if bending upward, of course, the positive bending moment. Above, you have the contraction and strain, stress, elongation all should be positive. And below is elongation. When y is negative. And so this negative sign is just to make sure for positive y, it has contraction. For negative y, it has elongation. And that is all about the strain. And for the stress, since we only have one non-zero stress component, the relation between them is the Young's modulus. So now this is the relation of how the stress change in the y direction, and this is the stress distribution is always zero at the neutral axis or neutral surface, and the linear change in the y direction. And you can, this one is maximum compression, maximum tension. And some students came to my office hours said this part, why did we do this part? The x component is the force in the x direction. We know that when it's a pure bending situation, we don't really have the tensile force applied in the x direction. We may have later, like in the later chapter, we combine tensile tension compression, torque, transverse shear, bending on a single structure, and you need to calculate the stress and deformation response. But for now, we separate everything. So for this one, we only have a couple applied. So there's no force in the x direction. So, and also for the force, we know that force equals, if it's the stress, it's uniform distributed, is equal to the normal stress times area for tension compression. But since the normal stress sigma x is not uniform distributed, so it's linear change, so it becomes integration. So integration of the stress of the cross-section area become the force. And now we know that the force in x direction is zero, so this term should be zero. So we plug in the sigma x we just derived, and we get this one equal to zero. So this explains that why the neutral axis should always be on the cross section should always be the origin of the coordinate system or the centroid of section. Because in the statics we learned that this is the equation to find a centroid section, and you see that when this one equal to zero, this one equal to zero, this one equal to zero. So it should be the same point of the neutral axis on the cross section or the centroid of the cross section.
I have a question.
Yeah.
I'm not understanding why sigma x is the only non-zero. But at the same time,
based on our assumption, if the angle, we talk about the definition of shear strain is reduction angle after deformation. And if we consider before and after deformation, this angle maintains 90 degrees, which means that reduction of angle is zero. Makes sense or not? If reduction of the angle equal to zero, it means that the strain, they are zero. And since the relation between stress and strain is shear modulus, tau equal to shear modulus times gamma. So strain equal to zero, stress equal to zero.
okay, and then okay, so then what you were just going over now, I'm still confused on what the centroid has to do with figuring out why the force is equal to zero, or what does the centroid have to do with finding the integral of the x component?
When we say that below the neutral surface or above the neutral surface, how do you know where is the neutral surface? You need something to figure out the location of the neutral surface, and right?
It isn't. So you're giving us two ways to figure out the neutral surface, because you also said it's where strain and.
I'm saying that property of neutral surface is the sigma and the epsilon equal to zero on that surface. But mathematically, I give a cross section. How do you find the neutral surface? How? Centroid. That's the purpose I'm showing this part here. It's the same point on the cross section. And now you find the centroid, the cross section. Now you can say, okay, on that neutral surface, stress, strain in the x direction equal to zero. And if bending upward, above the neutral surface, it has compression, and below the neutral surface, it has elongation, tension.
Okay, I think I understand. So the centroid formula that we learned in statics is a tool that we can use to find the neutral surface.
Yes, correct. Yes.
And for the integration that you were doing before, you're just reinforcing the idea of how we find the centroid?
Yes.
Okay. Thank you.
Okay. So we know that once we find the neutral surface, of course, we have all the property like how to calculate the stress, strain, and everything. We'll later learn this class. Radius curvature is also considered part of like how the bending deforms. But first, of course, we need to know where the neutral surface, like stress and strain equal to 0 on neutral surface is the property of the neutral surface for bending. But where to find it in the first place? That is from the centroid, right? And we know how to find the centroid of a cross-section in statics. We learned that in statics before. So let's say when you see a problem with complicated cross-section, of course, when you see a rectangle cross-section, you know, okay, neutral surface is in the middle. When you see a circular cross-section, you know that, okay, it's symmetric, so neutral surface is on center. But if you see something like this, trapezoid, or you have an I-beam, very commonly seen in real life. And I-beam, let's say the top and bottom flange, they're not the same length. It's not symmetric anymore. How do you find the neutral surface in the first place? And then you can say, okay, below and above neutral surface stress, how they change. But how do you find it in the first place? That is through finding the centroid first. We'll do a practice problem very soon. You do need to find the centroid first, and that becomes the neutral surface. And then you can do the calculation after that. So this is the whole point of having this part. And this part, this x component, some students asked during the office last time, x component is the force in x direction. Integration sigma x of area equal to the force in the x direction. And since we don't have tensile compressive force applied, this one should be 0. So this part. And for the moment about the axis, of course, we know should be equal to the couple applied. And it's also equal to integration of the, so this is if we take a small area, this becomes the force on that small area. And this is the moment arm. And why we have negative y? Because let's imagine this is a positive sigma x. This is a positive y. Since this is the y-axis, this is a positive y. And for this small area, let's use this. For this small area, this is positive y. This is let's say the sigma x out of this positive x direction. This is positive sigma x, and this will generate a negative moment. So that's why we have negative sign here. So now if we integrate this one of the entire cross section, we get the couple applied or the bending moment of the cross section. So plug in the equation for sigma x, we get this one. So now this one is the second moment of the area is also the moment inertia, and we get the key equation here, sigma x equal to negative my of I. And for typical cross section, I gave here. You can do the derivation of the class, of course, by yourself. Integration of y squared dA. For the circular cross section, this is the equation. And for the rectangle cross section, this is the equation. And I sub x means that it is bending about x-axis. So also students ask me during the office are like, what is like bending about x-axis? So let's say for this cross section, this is narrow rectangular cross section, and x, let's say, is in this direction. And the bending about x, you can just imagine is this is x-axis. Bending about x is your beam is wrapping around this x-axis. And if somehow I rotate in this way, now I still bending upward like this, then the equation for calculating the moment inertia changed. The B and H the switch because let's do it this way. If we have a cross section like this, let's say if we rotate like this, then this becomes B, this becomes H, and you are rotating. So let's say this is the y-axis. This is the x-axis. And you're bending about y-axis, IY should be HB cube. Right. This is the same thing. I'm just giving you, like, you just need to be careful when you use this one. The sub x is the axis that is bending about. Yes, bending about y-axis now, yes. Any question for this part?
I have a question.
Yeah.
What is is the inertia a separate topic compared to the neutral surface, or what's the relation towards the inertia and the neutral surface? In terms of why we're discussing inertia, is that just a separate topic?
You need to know the moment inertia to calculate maximum shear stress or shear stress distribution. And MC of I or negative MI of MY of I is the moment inertia. You need to calculate moment inertia first before you calculate any stress distribution or finding the maximum normal stress. Okay,
and C is the maximum y distance that we can have, correct?
Yes.
There's no negatives, it's the magnitude.
The first equation is purely magnitude. The second equation considers tension compression. So basically, let's say if you have
it's compression when it's above the neutral surface and tension when it's below.
Yes.
Okay, I understand. Thank you.
You're welcome. So let's talk about this equation a little bit, because this is a equation you probably will use over and over again. Let's assume that if it's a positive bending moment, and if it's a point above the neutral surface, then mean that y is positive, then you will have a negative normal stress, which means it's compression. Right? This is the positive bending. And y positive means it's above neutral surface, and you will have negative stress. Same thing. Positive bending moment, if you have the point that is below the neutral surface, y becomes negative, negative, positive. So you have tensile normal stress, positive. But for this equation, it's purely the maximum magnitude of normal stress. There's no sign here. C is a distance, it's maximum distance. And we talk about the moment inertia, how to calculate moment inertia, and the thing you need to be careful when it's a narrow rectangular cross section, because bending about different axes, the way how you calculate the moment inertia is different. You need to know which axis is bending about and what is the B, what's the H. BH cube, which one you need to use a cube. And for this one and this one, you can consider, let's say this is a big circular cross section minus a small circular cross section. If it's a tube, and if for this box shape again, you can consider it's the big rectangular cross section minus smaller rectangle. And another thing is that we talk about the parallax axis theorem. So since you guys asked in the last class, but we didn't have much time, let's write the definition here. Parallel axis theorem is used for the, let's say this is a neutral surface or centroid. The line passed through the centroid. Since it's symmetric about left and right, this is the line that passed through the centroid of the entire cross section. And when this neutral surface is not overlapping with the centroid of the horizontal rectangular cross section and the vertical rectangular cross section, we do need to use parallel axis theorem. And this one is the individual moment inertia of each section. And this AD square becomes, let's say for this part, the AD square means the area of this one. D is the distance of its own neutral surface to the neutral surface of the entire cross section. So for the horizontal rectangular cross section, this becomes the D. For the vertical rectangular cross section, of course, the A is still this cross section area for this section, and D becomes its own neutral surface distance between its own neutral surface to the neutral surface of the entire cross section. Now this becomes the D. for calculating AD squared. So since you guys are asking last class, let's write down the definition. Move this equation here. The moment inertia about for an area about an axis, the axis here is x-axis, it's equal to the moment inertia of a parallel axis passing through the centroid, plus the product of area and square of the perpendicular distance between the axes. So equal to the moment of inertia about a parallel axis pass through the centroid. So this is this part plus the product of the area and square of perpendicular distance between the axes. So this is the definition of this term. So this is the details about the parallel axis theory. And of course, we have one example problem to help you how to calculate in this situation when the neutral surface entire crossing does not overlapping with the neutral surface of each individual section. How to use this parallel axis theory. So any question for this part?
I had a question.
Yeah.
Oh, sorry. What Ix prime, what axis does that relate to when you're talking about
So this is the moment inertia of the entire cross section. Let's say this is the x. This is a neutral surface. This red line is a neutral surface of the entire cross section.
Okay.
And it's equal to for the top part. And this blue line means the neutral surface, a line that passes through the centroid, or you can say if we only consider this top, this part, this is the neutral surface of the top part.
Okay.
So it's equal to the moment inertia of this part of this rectangle, single rectangle,
Sure.
about its own neutral surface plus the area of this one times d squared. dy means the distance between its own neutral surface to the neutral surface of the entire cross section. This is the d.
Okay. And I get you the moment of inertia for the entire shape.
Yeah, so you need to do the same for this one also. You need to do the same for this one also. So
Okay.
you have
And
the
then add them all together for the total one.
yes. Now you get the moment inertia of the entire cross section. Yes.
Okay. So you have to do them separately, not just one and done. You have to do it twice for each part.
Yes. Yes.
for each-
Yes.
Thank
Yes.
you.
If you have a I-beam like this, then you need to do for this one, and for the bottom part.
Thank you.
You're welcome. Any other question? Okay, let's check the example problem. Cross section is given, dimension are given in the figure. Couple direction is given. Determine the value of bending moment that causes the bar to yield. Assuming the yield strength is 36 KSI. How to calculate? It's like it's similar as, let's say, allowable normal stress is 36. What's the maximum bending moment can be applied? Is same as previous question. Normal stress equal to MC of I. Yes, thank you. Thank you. How to calculate I for this one? What is the B? What is the H?
Is B 0.8 inches
Yes, thank you.
and then H is 2.5.
Yes, thank you. So this is the moment inertia. Since the maximum stress is equal to MC of I, and we know the sigma m, the maximum normal stress, we can calculate the bending moment can be applied. So bending moment equal to the maximum normal stress can be in the structure times moment inertia of a maximum distance to the neutral surface. And this distance is, since it's rectangular cross-section is symmetric, so it's really half of the height. So we know that yield strength is 36 KSI. We use inch pound, so PSI. What did I see?
1.25.
Thank you. Inch.
What would happen for C if it wasn't a like a symmetrical cross section, or if it wasn't a rectangular cross section?
Good question. What if let's say something like this? You would expect the centroid somewhere like the neutral axis of this trapezoid shape. Let's say this is the neutral surface. Then this becomes the C.
So you'd have to calculate the centroid.
Yes, you for like well, as I said, for circular or rectangular cross section, it's very easy. We know that path through the middle point is centroid. Is a centroid neutral surface. The line is neutral surface. But for other shape, more complicated, you need to find a centroid first, and then this line becomes the neutral surface. The neutral surface, and now the maximum distance should be this one.
And what if the centroid is like higher up in the structure? So would it just be like C? Like what if the distance between the centroid and the bottom was higher than the top? You would just find the magnitude. The
Let's use this one as example, right? So for this one, you have this T-shape cross section, and you expect that of course the neutral surface is closer to the top, right? And then the C becomes, let's say this is the bottom line, and let's use a different color. Let's see the back color. Now this becomes the C. It's really finding the maximum distance. Now this becomes C. Makes sense or not?
Yeah, thank you.
You're welcome. Any other question? Thank you for the question. So this is like this example problem is like very straightforward application of the equation sigma equal to mc of I. Some students complain that our quiz and homework and exam is more difficult than the example problem in the class. Of course, the first example problem is always the easiest example problem I could think of, because I want you to see how to apply the equation like very straightforward way. So you do not expect that I will ask any exam question like this, right? Now let's see a more complicated example problem. What, you guys are unhappy about that? I'm making you guys ready for more advanced class, because if you only like this semester only make you ready to solve problem like this level, you will really suffer in the higher level class or in your future career. I'm the instructor, I decide whatever I want. You guys don't have a choice. You will thank me in your future career, like when you have a job interview with some structural engineer, when you need to have 1 hour conversation with a structural engineer, and they decide if they want to give you that offer, you will thank me at that time. You may hate me now, but it's okay. Second example, 2 vertical forces apply to a beam of cross section shown. Okay, these 2 vertical forces. Determine the maximum tensile and maximum compressive stress in portion BC of the beam. How to calculate this one?
Do you first calculate the centroid of the cross section?
Yes. Where is how to find the centroid?
You find the area, or you divide by the area, but I forgot what the numerator was.
Okay. So here. Right. For left and right, because symmetric, and of course, we know that for this cross section is symmetric left and right. So we know that centroid is definitely on this axis. But for the y direction, we need to figure out like where's the centroid. And so this is the equation. This is the equation. We need to have the y times each area, and the sum of the y times each area divided by the entire area. Let me show you how to find the centroid of this one using this example.
Well, I
So-
have a question. If we already know the y is guaranteed to be where the centroid lies, why are we finding the centroid for the y and not the x? Like you said, the midline is for obviously where the centroid is for sure going to be, and we're finding I guess like the horizontal direction. Wouldn't that be the x?
I may said something wrong. You definitely know that the centroid should be on this line, right?
Yeah.
Now you just need to figure out in the y direction. Where is the
Okay. Thank you.
You're welcome. So for this one, of course, we know that this cross section has two parts. One is we separate two. Let's say the bottom part is 1, the top part is 2. So it's y times the area divided by the entire area. So we have 2 section. One, 2, and for the area, for the bottom part, is 2 times 9. Area of the top part, the vertical rectangle cross section, 6 times 3. This part is easy. So the entire area is 36. And for the y, let's put this one as a reference line. This is not a neutral surface or anything. This is just a reference line for our calculation for finding the centroid. Oh. This is a reference line. So y bar for everyone is the distance of the centroid to this reference line, which should be equal to 1. The y bar for the second area, rectangle cross-section, should be the distance between the centroid and the reference line. Centroid, you should imagine should be of course, half the middle point. So it should be 3 plus 2, 5. This is the y bar for different area. And now, of course, we can have the y bar times a. That's how we find the centroid. So the first one for the first area is 18. Second area 90. So y bar times a equal to 108. Now, if you are getting lost here, let me show you this one again. The centroid in the y direction is equal to the sum of y times a for all different components. In our example, we only have 2. So it's y1 times a1 plus y2 times a2. Plus y2 a2. For our example problem, we only have 2 areas. So this one is the entire area, it's the area of the entire cross section. So it becomes a1 plus a2. And this is the location of the centroid in the y direction. So back here. Let's use y, uppercase y bar, a equal to, or let's write it this way, make it less confusing. Equal over the entire area. So it's 108 equal to 3. So we find the central in the y direction, and of course, we find the neutral surface of the entire cross section. If you see close on the bottom image, there's a thin line at the bottom. That's the bottom part. Yes, yes, yes. So let me see if I can do a demonstration here. So this is a cross section, and the figure above shows something like this, right? And the second graph is I rotate in this way. Now you see something like very thin structure at the bottom. This is the top graph. This is the second graph. Make sense or not? Where did the y bar value come from again? Y bar. So this is, you first choose a reference line. I choose this bottom line, the reference line. Of course, you can choose the upper line, this one as reference line. And then in the end, your centroid is a distance with respect to this reference line. Let's say I choose this bottom line as reference line, and y bar for area 1 is the distance of the centroid of the first rectangle to this reference line, which should be 1. The y bar for the second area is the centroid of the second area to this bottom line, which should be equal to half the 6, 3 plus 2, which is 5. Make sense or not? Okay, you're welcome. So now we have the neutral surface of the entire cross section. Let's put in a graph. This red line is the neutral surface of the entire cross section. Let's calculate the moment inertia. And of course, moment inertia, we need to consider 2 parts. Let's calculate each part separately. Try not to skip any step. I1 equal to B at B1 H1 cube plus A1 D1 squared. So what is the B1 and H1? What is B1?
What would it be, 2 inches?
What is the B1? I need to put in calculation.
2 inches?
2?
Or
Would it be 9?
Yes, it should be 9. It's bending about this axis, right? It's bending about this axis. Back to the equation, you can see that the B should be the dimension that parallel to the axis. So this equation is for bending about x-axis. So the B dimension is the dimension that parallel to the x-axis. That is a B. So back to our example problem, the dimension that parallel to this axis is 9 inch. And H is 2, of course. AD. A is 18. D is distance between its own axis, own neutral surface to the neutral surface of entire cross section. So what is distance? Let's say the neutral surface of its own cross section of part 1. This is the blue line. It passes through the center, of course, and the red line is neutral surface of the entire cross section. This should be what I did here. 2. Thank you. 2 inch. Because we already calculate that this distance is 3. When we find centrally, we already figure out this distance is 3. So we know that this is 1, so this is 2. Two squared. And similarly, we can do I2. Should be equal to 1 over 12 B2 H2 cube A2 D2 square. What is the B2? 3, thank you. And H2, of course, 6. And A2, 18. What is the D2? What is D2?
One.
Yes. No. Why is 1?
Oh, it's
What is the D2?
2.
Yes, thank you. So it's a distance of its own neutral surface to the neutral surface of the entire cross section. So it should be distance between these two, right? And of course, if you know this is 1 and this is 3, so this distance should be 2. Two square, 126 inch 4. So the moment inertia of the entire cross section, of course, is I1 plus I2 equal to and any questions so far? How to calculate the maximum tensile stress, how to calculate maximum compressive stress. Where the location has the maximum tensile stress? Where is the location that has maximum compressive stress? Yeah.
Would the maximum tensile be at the bottom and maximum compression be at the top?
Yes, yes. So let's say I use subscript tensile maximum. Should be equal to negative. It's negative MY/LY. It's about what Y should we use. And since he just said the maximum tensile should be the bottom surface, I use subscript bottom over I. Bending moment. What is the bending moment? Anyone? What is the bending moment should I use? Yes, yes, 15 times 40, yes. Wait, it's times 40 or times 60? You guys are confused. This is a statics problem. 40, yes, it should be 40. Y bottom should be negative. Make it positive. Yes, you're correct. The maximum tensile stress is at the bottom, and the bottom, Y is below the neutral surface, so Y is a negative value, and you have negative sign in front of the equation. Negative, have positive, you have maximum tensile stress. Yes. So for the maximum bending moment, it should be 15 times 40. It's not 15 times 60. If let's talk about the bending moment diagram you guys learned in the statics, how to draw the bending moment diagram. Linearly increase, constant in between, and decrease back to 0. This is the bending moment diagram of our beam. Make sense or not? And for this value, of course, is 15 times 40. Make sense or not? If you cut through here, let's say we cut through here, the moment equal to the force, let's say the reaction force here is 15. So you cut through this point. So equal to this force times this distance. This distance is 40. So it should be 40 inch pound. Y bottom. What should we use for Y bottom? Three. Very close.
5.
5. Why 5? Yeah, it should be -3. -3. Y bottom. This is the your origin of the coordinate system is here. This is below, so should be -3. And then in the end, you get a positive value, right? Become maximum tensile stress. 204 inch to the force. So everything is in pound and inch.
I have a question. If it was to find the max in general, then
Yeah.
then it would be 5, right? But since it's tensile, since the
Yes.
tensile is below.
Yes. If I ask you about what is the maximum magnitude of normal stress, then you need to use 5.
And it would be the same thing. And like in this case scenario, it would also be the max compression.
Yes. Yeah.
Right? Okay.
Yes, you are correct. So one more step, compressive maximum. -my. We know we should use the y for the top surface. I use subscript top, fi. The minimum is the same, of course. And the y top is 5. So it should be, let's drop a top line here. This one is 5. Makes sense or not? This is top surface. This is the neutral surface of entire cross section. And this should be 5. So you should plug in it's supposed to be 60. Okay, wait a second. What did I write? Oh yeah, sorry. I wanted to write 60 times 10 to the 5th, at the moment, but somehow I mixed everything. So it should be 40 force times 15. You're welcome. 204. So now this is negative. Any question? So in this example problem, we practice how to find a centroid, which is the location of a neutral surface. We use parallel axis theorem to find the moment inertia of the entire cross section, and then we practice how to use negative sigma equal to negative my of I to calculate the maximum compressive stress and the maximum tensile stress. And of course, if the question asks about what is the maximum normal stress, then is equal to the magnitude of this one. This is the maximum normal stress, magnitude of maximum normal stress. Yes. Yes, this is closer to something we would see on test or quiz, yes.
I have a question.
Yeah.
Why did we define our central axis? Can you go back up? Can you scroll back up? Why did we define our central axis? Right there. I was kind of confused. Why did we define it right there?
Why we define the red line?
Yes.
Well, before we do our calculation, we need to know where the neutral axis is. Otherwise, how can we do our calculation?
Yeah, but how do we know what the neutral axis is? That's what I'm asking.
Neutral axis is the centroid of the entire area. This is what we learned in the statics, how to find a centroid of the entire area. And we already proved centroid is the line that passes through the centroid is the neutral surface in the entire cross section.
Okay, thank you.
Welcome. What if there was only one force in the middle? Would divide by 2. That's a great question. What if there's one force in the middle? What if it's something like this? Again, if cross-section everything is the same, the only thing changed is maximum bending moment. And we know that this point should be the maximum bending moment, right? How to find the maximum bending moment here? So let's say if the force is 1000 and this distance is the entire beam is 10. What is the maximum bending moment? Anyone?
4,000.
5,000? Let me show you the calculation here. Okay, so all the answer in the chat, they are 5,000. What the reaction force here? What the reaction force here? 500. 500. I guys agree with me or not? If you have 1000 applied at the middle point of the beam, then the reaction force here is 500, 500. Do you guys want to change the answer or not? What is the maximum? What is the maximum bending moment? I think we got a correct answer there. So it should be 500 times 5. Moment arm is half of the entire beam length. So it should be 2,500 Yes, you are correct. Yeah, so if you need to leave, of course, we're done for class today, but if you have any question, you can stay and ask. Any question? Yep.
Yeah, I got a question.
Yep.
So back to the problem we were just doing. It's like a T-bar with like the middle skinny part and then like the lower fat part. What
Yeah.
if there was like another, so if instead like a T-bar was an I-bar, so like there's a fat part on both sides, what would we use as our Y-bar when solving for tensile strain? Or sorry, tensile stress.
So thank you for the question. So let's say if it's I-bar, right?
Yeah.
If it's symmetric on the top and bottom, then this one becomes very easy. Let's talk about the symmetric I-beam first. If it's symmetric, then actually this problem is easier than the example problem we have solved, because now the neutral surface, well, the moment inertia you can simply use this one minus this one minus this one, right? You get a moment. You don't need to use parallax theorem. And again, for this one, if it's symmetric top and bottom part, the magnitude of maximum compressive, the magnitude of maximum tensile should be the same. So the top surface will have the maximum compressive stress. The bottom surface should have the maximum tensile stress. And since it's symmetric, the C here should be the same. So the magnitude of these two should be the same. Make sense or not?
Yeah, but then the compressive would still be negative because it's on the top surface, right? Not the bottom.
Compressive is always negative. That's our sign convention. Whenever you see compressive, the strain, stress, internal force, delta, it's always negative.
Okay. All right. And then a quick second question is when do you think the quiz grades are going to be out?
1 week.
Okay. All right. Thank you.
You're welcome.
All right, yeah, I had more of a status question.
Yes.
When we about the diagram, about the maximum moments diagram. I'm sorry, I was kind of confused about that part still. Kind of forgot some stuff. How is, for example, I understand that at B is 15 times 40 because of the moment arm.
Yeah.
But if both of them are pointing in the same direction, so like at C, 15 kips are also going down. How does that moment not increase? Is that because the reaction at D kind of
You are talking about why this section is constant, right?
yeah, why is that constant? Yeah.
What is the way you guys do the bending moment diagram? Let's say if you want to know the bending moment diagram of this section, and for a random point, you cut through this point, right? You cut through this point. And so you know that, okay, reaction force equal to 15. And cut through random point, let's assume this is x. So the moment is equal to 15 times x. And since it's 50 times x, so we know that it's a straight line. And when you cut through this point, you see what I mean? The moment is only for this, from this point to this point, this nothing can increase the bending moment in the section. The moment is only created by this couple. So it's 15 upward, 15 downward. Distance between them is 40. So this one generates a moment. And that is a moment at this point. And you get into this direction in the BC section, there's nothing really increases couple or increases bending moment. That's why it's constant. Of course, you can use the equation. You cut through a random point in the BC section, and you do the free body diagram and equilibrium equation. You have the equation of bending moment through the BC section, and you will get a constant value. Right. And now you go through in the CD section, of course, you can use the left side or you can use the right side. And of course, use right side will be easier for doing the free body diagram equilibrium equation. And same thing, reaction force here is 15. And this distance now, if you use X, it doesn't matter, it's moment arm. So it basically means that as you distance increase from the D point, the moment arm linearly increase. Yes, the method we learned in the statics is purely based on cutting through a random point through that section. And to the free body diagram equilibrium equation, you have the expression for bending moment diagram. And if you do that for the BC section, cutting through random point in the BC section, you will get a constant value. And of course, in our class, mechanics material, we have a easier method to draw the bending moment shear force diagram we'll talk about later.
Thank you.
You're welcome. Any other question? Let's see any question in the chat. If T bar was if T bar was rotated 90 degree, would yes, you're correct. If it's rotated 90 degree, then B and H should be swapped. If we choose a reference line to be at the top, would I still get it correct? Yes. So of course you can use the top line as a reference line, and then you have different Y bar for area 1 and area 2, and then in the end the 3-inch should become 5-inch because the location of neutral surface should be the same as long as your calculation is correct. But it's just like with reference to the bottom line, you get 3, but with reference to the top line, you get 5. But it represents the same location of neutral surface. Make sense or not? Okay. You're welcome. Any other question? If no question, I'm gonna switch to the office hour Zoom link, and you can come to my office hour for any question you have. Thank you for coming and have great long weekend.